Imagine a world where the hum of an electric motor isn't just background noise, but the sound of a revolution. This isn't about batteries or charging speeds. It's about something far more fundamental. It's about motion itself. Deep in an Oxford lab, far from the spotlight, a single sketch changed everything. No fanfare, no corporate backing, just an engineer with a question. What if the electric motor, a machine perfected over a century, still had untapped potential? That question led to a breakthrough so powerful it now sits inside Lamborghini's fastest cars. But this isn't just a story about speed, it's about reinventing the very heart of propulsion. Why are the world's most elite automakers ditching tradition for this radical new design? What makes this motor different from every other electric engine on the road? And how did a forgotten concept from academia become the future of high-performance engineering? The answers lie in a quiet lab, a stubborn engineer, and a motor that defies every rule. In 2005, inside the University of Oxford, a PhD student named Tim Woolmer was wrestling with a problem few cared about. Electric motors were heavy, inefficient, and limited by their own design. The industry had accepted these flaws as unavoidable. Woolmer didn't. His obsession wasn't horsepower or raw speed, it was efficiency. Every motor he studied wasted energy in ways that seemed fixable. The problem? Iron. Traditional motors relied on thick iron cores to guide magnetic fields, but that iron added weight without contributing to power. It was dead mass, and Woolmer was convinced there had to be a better way. By 2009, he had his answer, and a company to build it. YASA, short for yokeless and segmented armature, was born not in a flashy startup hub, but in the quiet corners of engineering rigor. While others chased battery breakthroughs, YASA focused on something far simpler: torque. Not just any torque delivered in a way no one else had mastered. The secret? A design so radical it seemed impossible at first. Most electric cars use radial flux motors, where magnetic fields radiate outward like spokes on a wheel. It's reliable, but inefficient. Woolmer's motor worked differently. It used axial flux, a design where magnetic energy flows sideways like two spinning plates pushing against each other. The advantage? Leverage. Just as a longer wrench gives you more twisting power, magnets placed farther from the center generate more torque. Axial flux motors exploit this, packing more punch into less space. But there's a catch. The farther components are from the center, the harder they are to control at high speeds. Stress builds, materials strain, and most axial flux motors fail before they can prove their worth. That's where YASA's real innovation begins. The name isn't just branding, it's a blueprint. Yokeless, segmented, armature. 3 words that rewrite the rules of motor design. In a traditional motor, the yoke is a heavy iron shell that holds everything together. It's sturdy, but wasteful. Woolmer's breakthrough was removing it entirely. Without the yoke, the motor shed weight dramatically. But how do you keep everything stable without that iron backbone? Advanced materials and precision engineering. A structure so carefully balanced it doesn't need the crutch of excess metal. Then comes the segmented armature. Instead of solid copper windings, YASA's motor breaks them into individual coils. This does 2 things. First, it eliminates wasted copper. Every strand sits perfectly within the magnetic field. Second, it opens channels for cooling, letting heat escape instead of building up. The result? A motor that's lighter, more powerful, and more efficient all at once. Most engineers would call this impossible, too fragile, too complex. But Woolmer proved them wrong. By 2015, YASA's motors were turning heads in the auto industry. Ferrari took notice. Koenigsegg pushed the design further. Then came Lamborghini. Not just adopting the motor, but rethinking the entire car around it. The Revuelto isn't just another hybrid supercar. It's a showcase of what axial flux can do when unleashed. Three YASA motors work in perfect harmony. Two up front, each independently controlling a wheel. No mechanical differential, just pure, instant torque vectoring. The third motor sits inside the V12, nestled between engine and transmission. No lag, no wasted motion. Just seamless power, blending combustion and electricity into something entirely new. The numbers defy logic. Each motor weighs just 17.3 kilograms, thinner than a laptop, yet pumping out 148 horsepower. Three of them add over 440 horsepower without the bulk of traditional systems. The battery? A mere 3.8 kilowatt hours, tiny by EV standards. But it doesn't need to be bigger because every watt is used perfectly. This isn't just engineering, it's artistry. Every gram, every wire, every magnetic field optimized to do more with less. And that's what makes it dangerous. Because once you prove a motor like this can work in a Lamborghini, the entire industry shifts. Electric planes, motorcycles, robots, all hungry for compact, torque-rich power. YASA didn't just build a better motor, they built a new way to move. And it all started with a sketch in a quiet lab. The true power of YASA's motor isn't just in what it does, but in what it makes possible. This isn't just a component swap, it's a reimagining of mechanical design. Every industry that relies on motion is watching, because when you crack the code of torque density, everything changes. Take aviation. Electric planes struggle with weight. Every gram counts when you're fighting gravity. A motor that delivers massive torque without the bulk, that's not an upgrade. It's a revolution. Or robotics. Machines that move like living things need actuators with precision and punch. Traditional motors are either strong or nimble, rarely both. YASA's design could bridge that gap, but the real shockwave is in scalability. For decades, axial flux motors were lab curiosities, too finicky for mass production. YASA proved they could be built reliably. Now, they're proving they can be built fast. New factories, streamlined processes, materials engineered for volume, not just prototypes. This is where the quiet Oxford idea becomes a global standard, and it's happening sooner than anyone predicted. Lamborghini was just the beginning. Mercedes-Benz acquired YASA in 2021, not to shelve the tech, but to accelerate it. Their goal? Mainstream electric cars with unprecedented range and performance. Because when you shrink the motor, you free up space. Smaller batteries, lighter chassis, more room for innovation. This isn't about making cars faster. It's about making them smarter. But let's peel back another layer. Why did radial flux dominate for so long? The answer lies in inertia, both mechanical and mental. Radial motors are straightforward to manufacture. Coils wound in place, iron cores stamped and stacked. It's a system the industry understood. Axial flux? It demanded fresh thinking, precision alignment of magnets. Cooling systems that work in 3 dimensions. Materials that could handle stress without bulk. For most companies, that wasn't a gamble worth taking until YASA showed the payoff. Now, the calculus has flipped. The motor's elegance lies in its simplicity. Fewer parts doing more work. Magnetic fields harnessed, not just tolerated. Heat managed, not just endured. Its engineering is minimalism. Strip away everything that doesn't serve a purpose. That philosophy extends beyond mechanics. Think about energy grids, industrial machinery, even wind turbines. Anywhere electricity meets motion, YASA's principles could rewrite the rules. But here's the twist. The biggest impact might not be in the machines we see, but in those we don't. Drones that fly longer, medical devices that fit in the palm of a hand, Subsea robots exploring depths untouchable by clunky, heavy motors. This is the hidden promise of Axial Flux, liberating design from the tyranny of weight, yet challenges remain. Scaling production without sacrificing precision. Pushing thermal limits even further, integrating motors into ever more unconventional spaces. YASA's team knows this. Their patents aren't just about the motor, they're about the ecosystem around it. Cooling loops that double as structural elements, software that tweaks magnetic fields in real time, materials that blur the line between conductor and insulator. This isn't iteration, it's reinvention. And it's happening while most of the world isn't looking, because revolutions don't always roar. Sometimes they hum, a quiet vibration in an Oxford lab, the whisper of magnets doing more with less. The sound of an industry pivoting one motor at a time. What began as a sketch is now a benchmark. Lamborghini's Revuelto is merely the first chapter. The next? Cars we can't yet imagine. Aircraft that defy current physics, robots with the strength of giants and the grace of dancers, all because one engineer refused to accept good enough. That's how change happens, not in boardrooms, not in splashy headlines, but in the stubborn pursuit of a question. What if? And the answer, it turns out, was hiding in plain sight. In the space between magnets, in the flow of fields we can't even see. In the belief that the future isn't just about more power, it's about better power. NASA's motor isn't the endpoint, it's the spark. The rest? That's up to the next generation of engineers, the ones now sketching in quiet labs, unaware their ideas might one day move the world.